Hello everyone, in this tutorial I'm going to show you how to model a 3D bracket pin in Abacus. So what we're going to do, we're going to model the first part on the right side of this assembly in Abacus, and then we're going to import the pin and also the left side from the other CAD software that I modeled those in SolidWorks. So we're going to import them, and then we're going to assemble it and apply pressure on one side, we'll fix it on the other side, and you're going to see how you can actually have the combination of the assembly, that part of it is made in Abacus and part of it come from the CAD software. Now let's start making this the right side of this assembly in Abacus. Part section by creating a new part. I'm going to call this one bracket, and it's going to be 3D deformable solid and extrusion, and I'm going to use a millimeter unit system. So the approximate size, I'm happy with 200. Click on continue. Now I'm going to create the construction lines, so one from here to here, one from here to here, and I'm going to fix these ones both directions, and then I'm going to draw a circle on one side, and I'm going to give it radius to this one, so it's going to be 22, and I'm going to draw a line from here to here. Don't worry if it's not straight, because later on you can make that correct. And I'm going to give a dimension from here to here, should be 38, and I'm going to do the same thing from here to here, and then I'm going to use a trim to get rid of the extra lines. So now from here I'm going to use a tangent, and I'm going to click on this one and this one and this one and this one. Okay, so I only need to give a dimension again to this one, because once I removed the extra line, the dimension was gone. So now I'm going to do the other side of the this bracket. So I'm going to just draw a rectangle. Again, as I say, it doesn't matter if it's not straight, because we can use the horizontal and make this one straight. Okay, so again from here to here is going to be 64, and I'm gonna use a fillet, and so the fillet radius is going to be 14, and we have to select two lines from here to here and here to here. So I want to draw a line, but I have to make sure that the distance is correct. So that's 8. I'm happy with that. So I'm going to just draw a box to here, and then I'm going to use horizontal again. And I know that the distance from here to here is 20, and I'm gonna draw another circle from here to here and get rid of the extra lines. Okay, so again I'm going to use a tangent also from here to here, and again using this command to get rid of the extra line. And we have another small circle here in the middle, so I'm going to give a radius to this one. That's going to be 11. So now I'm done with my sketch, so I'm going to just save this one as a sketch 1, and now I need to extrude this one. So I'm going to extrude this one 52 millimeter. So next step is to basically transfer this one to so as you can see, we have to get rid of the top section and also the section in the middle. Okay, so I'm going to start from here, this side, and I'm going to use the extrude cut, and it's very important, instead of auto calculate, use a specify, and select this surface, and I'm happy with the 0 0, and I'm going to change this one to horizontal, select the top one, and now if I bring back my sketch, click on OK, you see that my sketch is located exactly on the top of the previous model. Okay, so now here I am gonna draw a line from here to here, and I'm gonna get rid of everything else on the left side. So now I can extrude cut this one down, and so I don't want it to be through all, so I'm going to go to line and I can give a depth to this one, and that's going to be 32. Okay, now the next step is to do the left side. For left side, I'm going to create a datum plane. So by offsetting from the bottom one, and I have to give a value for this one, so I'm going to give 16, and then I'm going to create my sketch on the top of this. Again, I'm going to use extrude cut, make sure that's unspecified, select the datum plane 0 0, and I'm going to do horizontal on the top, select this line and bring back the sketch again. So now this time I'm going to do the left side. I just need to have the dimension from here to this line that I create. So from here to here I want this distance to be 13, and then I can get rid of everything else. Okay, and then click on done, and I can basically flip this one, and 20 is okay. So that's our model basically. Right, so we are we have this bracket here. What I'm gonna do next step is to import the rest of the parts that I modeled in CAD software, which in this case I use SolidWorks to model those parts. So when you want to import a CAD file, so you can right click here, and instead of create, you basically press on import. And here in import section you have different formats. There are not a lot of them, so you're limited with IGES, step file, or Parasolid. I quite like the Parasolid one because it makes the huge file quite small, so you're not going to have a huge file in this case. However, each of these will have its own license, so you might be able to import it as a step, but you're not be able to import it as a Parasolid. So it really depends what license do you have and which one you can use for your model. I'm generally happy also with a step file, so I've never had the issue with it. So I recommend you to use step or a Parasolid depending on your license. When you want to save your CAD file, make sure that you save them in a C drive. So as you can see here in Abacus, you can only see the your drive. So in this case I only have one, but for instance, if you save your file on a desktop, you won't be able to find it in directory, so you can only find it in the C drive. So you can download these two files from resources section, and once you download them, put them in your C drive or any other drive that you can see from the directory at the top, and import the first one, which is part 1 step, and click on OK. Once you do that, then the software will ask for a name and the part file. So currently I'm importing a part individually. So what does that mean? If I had assembly in a CAD software, and if I wanted to import it into Abacus, I have two options. I could make that assembly as a single part, and that's useful, for instance, if you have one type of material. So if you have 20 parts, you don't have to individually go and give a material to those 20 parts, so you can just combine them. However, if you actually have a different material and the contacts are important, then you'll use create an individual part. I've seen that many people using the CAD software, and instead of modeling it in the part section, they model it in assembly, so they would have quite a lot of part. However, their model is just a single part, but they use the model it in assembly. In that case, so you have to use a combine into a single part, so to have it here rather than in the as a create individual part. Because I mean, I've seen people they model this in SolidWorks, and they do the bottom part, they do the top part, and so 3 sections. So that means that when you want to import it as a create individual, you will have 3 different parts, which is wrong. I mean, this is a single part, so then you have to use a combine into a single part. Then here you can actually say what sort of modeling space you're going to use. So obviously it's going to be a 3D, and the type is quite important as well. So if you're importing a file into Abacus that you want to use it as a discrete rigid body, then you can use that, or even Eulerian. And then we have a scale. So this scale is again another important part in Abacus. You have to basically, because you don't have a unit system, and you have to take care of a unit system. And in a CAD software, obviously you would have a unit system, and you know about that. Obviously, you know, options, all the CAD software, they have an option that you can go and check the unit system. So currently I modeled my file in Abacus in millimeter. So, and also I did that one in a CAD software in millimeter. So if I import it as a donor scale, so they should be similar to each other. The best way of checking that is basically assembly. So if you have many parts, so currently I have 2 parts. So I import the first one, which is said do not scale. So I have this one. The best way to check that if your scale is correct or not is to basically go to assembly and import first the bracket that we have, okay, and then we import a part. So that looks like so when I check them, it seems that they are correct. So the scale are correct. So I'm happy with the scale of these two. So this is the way that you need to basically check if your file is correct or wrong. So if you have like suddenly 10 parts, don't import them suddenly. Also, if you don't have a reference model like the one that I have here as a bracket, and you want to import all your files from a CAD software, I recommend you to create a reference part, and that could be a simple box of, I don't know, 10 millimeter by 10 millimeter, and do the same thing in Abacus in a CAD software, and import those two first to see that if those two boxes are similar to each other, and if you are 100% sure that the unit system is correct, then you can carry on and import all the files and remove the reference one. That's the way that I always do to make sure that the unit is correct, because in Abacus there's no unit and you have to be very careful of that. So I'm going to import this part 1. I'm going to activate the auto offset, so I will have it on the right side, and then I will do the same thing for the pin as well. So I'm going to import this, and this time I'm going to import part 2, and again I'm going to keep it as it is. Okay, click on OK. So another important thing is the name of these. So when you import these names, and make sure that you keep the name consistent, especially when you assemble a file. So if you assemble a file and for any reason you think that, oh, the assembly is I'm not happy with the model, and I have to go to my CAD software and edit that file, and if you and you can basically remove that file, and if you try to so let me just demonstrate this. So if I try to rotate this one, and so it's going to be around the x-axis 190 okay. So first of all, I'm gonna basically put this one in this section, this empty section, and I can use the constraint coaxial and select this one and this one, and I'm gonna just flip it, click on OK. So as you can see, now we have this one there, and then I can use the there's going to be a parallel face, and I'm going to say this face and this face are parallel to each other. As you can see, now they're correct. So now I can move this face to the bottom face, and if I go here, use the face to face constraint. So first you need to select the moving part, which is going to be this face, and then the fixed part, and I'm going to change the arrows, and the distance between these two faces should be 0. So as you can see, now they're touching each other. Okay, so now let's imagine that for any reason that I made a mistake, and I decide to basically I'm not happy with this, and I'm going to get rid of this one. So if I go to a part section and I get rid of this, and this part 1, so So in assembly I still have this part as a part 1, but then if I try to import this as, so let's imagine that we do a modification and we import it and we don't change the name as a part 1, and if we go to assembly, you'll see that the part is still has its location, and this is quite important, especially if you do a small modification. Obviously if you do big modification, then you have to do assembly again, but if you're doing a small modification, let's imagine that this, the hollow in the middle is you're going to increase it by 1 or 2 millimeter. In this case, yeah, you can use the same geometry, and if you keep the name, then you won't have a problem with that. So now next step is to import the part 2, again the activate auto offset. First we have to rotate this one, and so I'll use this one, select this, rotate it along the x-axis. So I'm going to make this one 190 degree, and then I'm going to use the same coaxial, select this face and this face, and so click on this one, and then I'm gonna select the face, the top face, so face to face, and I'm gonna select this one, I'm gonna select this one, and let's flip this one. So if I click on OK, the distance should be 0. So as you can see now, they are touching each other at the bottom, and the assembly is completed. So this is assembly that we have completed. So part of it comes from Abaqus and part of it comes from the CAD software. So I hope that you understood the concept behind how you can assemble a file in Abaqus using a CAD software. Now let's create a property for this one. So we're going to just do the simple one for this. So let's just consider it to be still, and this is a megapascal, so that's going to be 210,000 megapascal, Poisson ratio 0.3, and we create a material property for this one. So let's call this one still and homogeneous, and the material is going to be steel, and we can apply this one to this part. So this one, and then I'm going to go to bracket, apply same thing to bracket as well, and part 2 pin. So we are done with assembly. Apply the assembly to all of these parts. Now assembly is done. The next step is step. So when you do this type of simulation, it really depends what you are looking for and how much displacement you apply. In this tutorial, I'm going to apply a small displacement because generally this type of simulation are quite heavy simulation, and because we don't have any sort of damage criteria, we might have a convergence issue. And so if you're applying a large deformation, and you want to basically, when I say large deformation, I mean above like 2 to 5 millimeters, something like that, then you have to use explicit solver. If you're using a static solver, you would definitely have a convergence issue with this one. So using a dynamic explicit quasi-static simulation is a useful solver for this type of problem. Obviously this type of problem is quite advanced, and so I'm not going to cover them in this course, but my other course in Udemy, you can actually see the bolted joint failure. So there is a similar type of geometry that we have all the damage criteria that we use dynamic explicit and quasi-static to have a failure in a bolted area. But obviously in this case we keep this course simple because this is just simply just for beginners. So if you are confident enough, then you can try the other course with a more advanced example. So let's keep this one static, and so we can turn on a nonlinear setting if you have a large deformation. I mean, however, you don't have a large deformation, but you can keep it on and if you want to change the displacement later in your model, but just be warned that it might take a very long time to run a simulation. And we have to turn on automatic stabilization as well, and keep the parameter as it is, but this will help with the convergence. Again, if you haven't watched the fundamental section, please watch that one that I explained these parameter individually there. For increment, let's make a increment size 0.1, and maximum number of increment, that's fine. I'll keep this one as it is. Click on OK. So the next step is interaction. So now we have to create a contact between these parts. So obviously, one easy way of doing that is to use a general contact. And so basically, once you define these, anything that they have a contact with each other, basically Abacus will define a contact between them. But there is another way of doing that, is to use the find a contact pair. So this is something new that you're going to learn in this course. And if you click on the find contact pair, basically what you can do, if you click on find the contact pairs, and the Abacus will actually find the contacts for you in this model. So if you look at this one, so as you can see, the contact is between this face and this face, which is not actually a contact. You see that they are quite a big distance now, because it's 3.16 millimeter. And then we have the contact between these two faces, which is correct. And then we have the bottom faces, again correct. And so the inner part of the circle with the bolt, that's correct as well. The top part of the bolt and the top face, this is correct. And this is basically for the right side, the bracket. So contact between the bolts and the right side of the bracket. And this is the bolt and the bottom face. And finally, this one is basically the bolt and the middle part. Okay. So once you do this, then you also have to define a contact property. So currently we don't have a contact property here. So if I edit a cell, then I can actually generate a contact between these. So if I click on contact, so I can define a different type of contact. In this case, I'm going to keep it simple. So it's going to be tangential behavior. So I can you can either make it frictionless or with the penalty of, so you can give a friction coefficient. So in this case, I would give 0.1, and normal behavior. Obviously, you can make it more complicated by defining a damage. If you use any sort of, let's say, if you have used a bolt and adhesive, so here you can define a damage here, and basically you can define the interface properties for adhesive that is located between a bolt and these brackets. Okay, that's a one way of doing it, but obviously this is very advanced. You can define a fracture criteria, cohesive behavior. Again, this is used for adhesive quite a lot. And so if you really want to learn these things, so you can check out my other course, which is more advanced. It has more advanced examples. So we are happy with this two simple contact property. Click on OK. So as you can see, the property is located here. Also, there are obviously some rules that you can define. For instance, as you can see, include a pair within a separation tolerance of 5.06. So currently mine is 3.16. So that's why Abacus found the contact between these two. So if I reduce this one, let's say if I say 0, then it wouldn't consider this as a contact. Okay. And also you can change the name. You can define the domain. That if you define a domain, it will just find the contact in those areas. Then you can also define a name for it. As you can see, it starts with SP. SP. So that's the name that you can change. Entities, like you can say that what sort of geometries you are looking for. So currently it takes everything. So solid, shell. Obviously this is quite useful as well if you have a combination of the shell and solid, and you only want to find the contact in a solid part and you don't want in a shell part, so you can deactivate these. So as you can see, SP-line base, cylindrical, planar. So you can basically modify this and tell Abacus where to look for a contact. Rules, you can define rules here for contact pairs and advanced. So here also you can ask to merge the pairs when the surface are within an angle of 200 degrees. So I mean, if there are within an angle of 200 degrees, the abacus will merge the contact between those areas. Okay. Again, obviously there are quite a lot of options here that we basically use them when it's required, but in this case it's quite simple, so we don't need to use those features. So now I'm happy with this, and so what I'm gonna do before closing this one, another thing to mention that we have at the bottom here the master and slave option that you can see here, and obviously this is another one as well that you can basically define the node to surface or surface to surface. So, and also the type of the sliding that you have, it can be finite sliding or small sliding. So this is another option that you can define, and then let's see the type as well. So the type, it can be interaction or it can be tie. So the interaction, obviously what we have done, when you do interaction you have to define the properties, and when you do tie, that means there is a perfect contact, and so there's not going to be a separation. But when you define a surface, that means that they are not basically attached to each other, and if you apply a force they may be detached. But once you put it tie, that means that the perfect contact between two parts. And generally tie type is much easier to get the convergence than the interaction. Interaction is always difficult, but it's more it's closer to the reality, real condition I mean. So I'm happy with this and click on OK. So once I do that, as you can see, I define the contact between these, and so what I can do, I can go to the contact. So I don't want this because this is something that there's no contact, and I know that because my model is in tension, these two faces, they're not going to touch each other. So what I can do, I can right click on this and suppress this one. Okay, so that's a way of basically once you find the contacts, if you're not happy with any of them, you can suppress or resume it later. Okay, I think I'm done with a contact as well. The next step is to go to load. So what I'm gonna do, I'm gonna fix one side by going here, and I'm gonna fix these faces. And in all direction, and also so there's no degree of freedom there. And then I apply a pressure on the other side. So I'll use the pressure, and I use this face, apply it, and so if it's uniform, that means the unit system is megapascal, and let's apply minus 5 megapascal to this part. So now let's go to mesh. So in mesh section, because we imported our model as a dependent, so we have to mesh them individually. And so as you can see, we start with part 2, and the part looks like a brown, and that's not a good sign. That means that you cannot apply mesh to this one using the hex or hex dominated. And the only way of basically applying a mesh to this one is to basically create a section cut, and without a section cut you won't be able to actually apply a structure mesh. The only way of doing that is basically using a tet mesh, and I'm going to just get rid of the mapped face, and if I apply this one, so as you can see, it will turn pink, and then we can apply a mesh to this one. So I can select this one, let's say 5, click on OK, assign a mesh, and then you will see that we will have a triangle mesh on this geometry. So now if I want to apply a kind of like a structure mesh to this one, what I can do, I can create a datum plane from here, create a datum plane, and if I select this face, enter value, and make this one 0, and for the top one the same thing, so select this one, enter value, and OK, and the distance 0, and if I create a section cut for this, so using the datum plane, so it will ask me, it's going to remove the mesh, which is I'm happy with it, and then I'm going to use this datum plane, create a partition, then select the top one, select the other one, create partition, and if I go here and go to here, Then I can use the hex one and use the sweep type. And if I assign a mesh, you'll see that you have this structure mesh rather than the triangle one. So you're going to have a hexagonal one. And obviously you actually need more section cuts to have that the top one. So if you do one from here to here for the top, from here to here, then you would be able to actually create a section cut for the top one as well. Also, what you can do, you can also change this algorithm, the type of the algorithm that Abaqus uses to mesh. So if you use a medial axis, sometimes it will give you a better mesh quality. So as you can see, this is the way that you apply the mesh. As I explained in the mesh section, it really depends on the application and the geometry. So there's not like a final correct answer will tell you which one is the best. So you have to basically check both of them and see which one you're happy. So you can even cancel the minimize the mesh transition and see the quality. So you see that it actually became worse in these areas. So you can have some random smaller mesh in those areas. So let's just keep this one advanced front, and I'll just select this. So the next step is to mesh part 1. This is the sweep mesh. So I apply this one to here, 5, assign a mesh. Okay, and again we can check this one. If I use the medial axis, what will happen to it? Okay, so when you look at this one, you see that the medial axis gave us a much better quality mesh in comparison to advanced front. So you see the difference. The geometry by geometry, the quality would be different. So you have to actually check the algorithm. Obviously, you can apply a structured mesh here as well by doing a section cut, and in this section from the line from here to here, and separate the top part from the bottom part. Then you would be able to apply a structure mesh to this. And the last one is a bracket. I'm not gonna actually section cut this one because it will take quite a long time to create a different partition. So you have to basically separate your model from here to there, and from here to here, and from here to here. So this middle section will be separate. So you will have 1, 2, 3, 4 section, and then you might be able to apply sweep hexagonal mesh. But in this case, let's just use a TET and free and use the default algorithm and just assign a mesh to this one. Let me see what size. So yeah, so the size is 5. It really depends on the power of your computer. So if you think that you're using a slow computer, I recommend to apply 10 as well. So not just for this one, you can do it for the part 1 and part 2 as well. But if you're using a faster computer, then you can even go lower than 5. But be warned that this is going to be quite a heavy simulation. Okay, so if I go to assembly, this is done. As you can see, we use the 2 different methods. So you use sweep here, and this is a TET mesh, triangle one. So I'm going to minimize this, and then I'm going to create the job for this. I'll call this one model 3 bracket, and so I'm going to just submit this job. And if it's okay, if it starts running, then I will show you the result from a completed work, because this will take I would say 20 to 30 minutes to get a result. So there is no error, so that everything is correct in our model. So what I can do now, I can go to this bracket simulation that I've already done and show you the result. So this is our basically simulated result for the this bracket. Some stuff you can do, actually you can basically use a remove selected. So if you select this one, and you can say what type of thing that you want to remove. You can say part instance, so you can actually select this part and you say you don't want that, and also you don't want this. So you can actually see the stress, what's happening in the inner part of the circle. and from the top here you can get rid of the mesh, let's say no edges, so you can actually see the stress values much better. And if you use the probe value, you can actually, if you go on a node, then you can actually move this one, and then you can record the von Mises stress on a different node region. Obviously, the finer mesh, the more number of the element that you're going to have, that will so you would have more information basically. Okay, and as you can see here, we have a high stress in this point because of this sharp edge, and obviously if we apply a fillet in this section, we'll get rid of that part. But the maximum stress is located in the fixed area at the top here, which is basically 49.36 megapascal. And we can see a displacement as well. So the displacement is quite small, is 0.067 millimeter. Also, we have some information regarding contacts. So if I go to CP RESS, which is for a stress, so you can actually see the value of the stress at the contact area, contact surface area. So you can see that the stress in this area is 10.75. So when you have a contact, Abaqus generally creates, so if I go to step and in here field output, edit this, so you can see that in the contact section we have a contact stress CSTRESS, and we have contact displacement, and so we have these two things that the Abaqus will actually show us in the visualization section. Obviously you can ask for more if you have so let's say at the contact force, you can ask for contact tangent direction, a contact status, and also I think that if you have some sort of failure, so this contact status will show that if you have a failure on the contact. So again, these things are available for you, and it depends really on the application and your simulation. The amount of the data that you give to the simulation as input will define the output. So it doesn't necessarily mean that I can select all of these things and expect that to have the result, because maybe I didn't provide the input for these data. But these are default that regardless of if you give just a Young modulus and Poisson ratio, you will have this information. So if I go back to visualization section, so you see that the first one is the stress, the contact distance. As you can see, this is how the opening will happen here. So that's very small. Also we have so this one I think is the tangential motion of the surface during a contact. So we have it in this phase and the top phase, so in two different directions. What also we can do, we can bring back this, and this time I can get rid of this, and also, so let's see if I get rid of, so let's just bring back everything. I'll just go to displacement and get rid of I'm gonna select the part instance, get rid of this one and also this one, and see that if we have any data available on this. So that's the stress, and then we have, so there is no information for these two, so there's nothing happening there. And let's see, okay, there's no shear as well. So if I bring back everything, and this time I'm gonna get rid of the middle part, and I'm gonna just look into the stress value at the surface. As you can see how the stress will spread in a bolt and this bracket, and then we can see the opening as well. So it's clear that there's going to be a the bolt is going to move, so there's going to be the opening between the contacts, and also this is basically a tangential motion of the surface during a contact. Okay, so while I was showing you this result, our simulation is done as well. So I can go back to this simulation here, and we can see that the simulation is done without any error. And so this is the end of this tutorial. I hope you enjoyed it and you learned in this tutorial how to use the automatic find contact, and also you learn how to basically combine models, some of them made in Abacus, some of them made in CAD software, and you assemble them in assembly section in Abacus. I hope you enjoyed this tutorial, and I hope to see you in the next video. Thank you so much for watching.